Hello and welcome to Postgres FM, a weekly show about all things PostgreSQL. I am Michael, founder of PG Mustard, and I'm joined as usual by Nikolai, founder of Postgres AI. Hello, Nikolai.
Hi, Michael. How are you? Let's not miss the fact that we have a guest today.
We didn't miss it. Just you throw things off by saying, how are you? And then I'm British, so I have to reply, how are you?
Well, let's blame the US. This is where I learned to ask. So I'm super glad we have Peter today. Hi, Peter.
Hi. Good to be here. Thanks for having me on the pod.
We are delighted to have you. And yeah, it's Peter Geoghegan. Hopefully everybody knows of Peter, but in case you don't, he's a major contributor and committed to Postgres for many years. 3 or so of the last were at AWS. So today we're going to be talking about some of Peter's recent and upcoming work on Postgres related to SkipScan implementation, but it's far more than that. And honestly, the more I learn about this work, the more excited I am about it. I thought I knew quite a lot, and I've been reading up in the last couple of days. And it's even better. Like, I didn't realize, and I'm probably cheating or skipping ahead far too much, but I want people to understand how big this is. This could affect our indexing strategies going forwards. We could be choosing to index Postgres differently. And that, anyway, I guess it's obvious in hindsight, but there's some real major differences. So yeah, I'm super excited about this work. I want to thank you for having started it and continuing with it. I'd be interested to hear, though, what attracted you to this work, and did you realize how powerful it would be when you first started on it?
Not at first, no. When I last did a similar interview to this, I think it was the predecessor podcast, technically, not this one. At that time, I happened to talk about how, for whatever reason, I kind of like finding as many different ways as possible of looking at a thing. At the time, I think I said something like, well, there's a bunch of different perspectives. There's the data structure perspective, there's the concurrency control perspective, and on down the list. And it was that sort of general mentality that brought me to this work, because I realized, hey, I'm missing something here. My tendency to sort of collect these different ways of looking at the thing, the same familiar old topic, this tendency I have, I was for a long time missing this extra bit, which I think is embodied by the work I'm doing now, and its source material, which is a pretty obscure 1995 paper. It happens to be called Efficient Search of Multidimensional Indexes. So you haven't heard of it, but hopefully that's not any indication of its real world relevance. It has been something that I believe has influenced a bunch of other systems. So it's, in that sense, I think, pretty standard stuff. But the implications, maybe, as you were saying, Michael, are not fully appreciated. So maybe we'll start with a general overview for those that don't know of what SkipScan is. It's a feature that certainly Oracle and in recent versions MySQL and also SQLite have. They all call it SkipScan. I think in DB2 it's called jump scans or something like that. So the basic idea is to extend the standard feature index access method to support new types of querying without changing anything about the on-disk contents, without fundamentally altering anything. This is possible with multi-column indexes, composite indexes. The simplest case, and the one that gets the most attention, is where you have an omitted prefix column in your query. So, for example, you do a select from a table where B equals, let's say, 5. Here we would have a composite index on AB. A, of course, has been omitted from the query predicate. So traditionally, in Postgres, at least, you wouldn't be able to really use the index. You might do a very inefficient full index scan where you sort of have to grovel through the entire leaf level of the index, and that works, but obviously that's not very efficient. What SkipScan will allow you to do here is, assuming that there are not terribly many distinct values in the column A, as a rule of thumb, I would say hundreds of distinct columns total, or perhaps thousands is about the upper limit, then you can effectively use that composite index as a collection of logical subindexes, they're sometimes called. So, for example, the first value might be 1 in the column A. So we'll do 1, A equals 1, B equals 5, A equals 2, B equals 5, A equals 3, B equals 5. And exhaustively, we'll do multiple small index scans that are effectively pretending to be one continuous index scan. And that will be certainly much more efficient than a sequential scan in most cases. Of course, it's true that you'd be much better off having column on B directly, but it's also true that who says that that's going to be possible? You might just not think to do it, or in some cases at least, it might not really be feasible. It much depends on the requirements for the user. This is particularly likely with things like data warehousing use cases, the fact table, where a lot of the querying is sort of ad hoc, and it's not really feasible to have all the indexes you might possibly require ahead of time. So here, it's making it a composite index much more useful for a wider variety of queries. If you only require adequate performance here, sub-second performance is attainable. It's not going to give you perhaps sub-millisecond performance, although that does sometimes happen, but it's still, for these kinds of use cases, almost as good. And yet it allows you to avoid creating a bunch of quasi-redundant indexes. So in that sense, as you were saying, Michael, it's kind of like it at least would require some of the conventional wisdom to be updated. I wouldn't say it's a radical shift, but there is a sense in which, okay, in light of this new capability, we're going to have to rethink some of the rules of thumb we have for indexing in general. I think that's likely to work out that way. I would say I'm excited to see how people end up using the feature in practice. Many things are possible. So that example I gave is a sort of very traditional, simple example, but also worth noting that the techniques that I'm working on include similar, though slightly different cases where, for example, you have a range. So suppose the query is select star from sales, where sales date between the 1st of August and the 10th of August. Then it could be that you're not enumerating every possible date in the entire table, but just those dates from that range, but the same exact idea still. So for the 1st of August, plus whatever the actual thing that appeared in your predicate in the query is, let's say, again, it's B equals 5, I don't know, that for the 1st of August, for the 2nd of August, for the 3rd of August. So from the query perspective, you haven't omitted the column. The column appears in this between range, but it is effectively the same idea. It also should be pointed out that these are all very general techniques. They could be combined in all kinds of different ways. And that's where it becomes super interesting. Like you have very, very complicated combinations of these things. The example query that I used to sort of, in my initial email to the hackers mailing list to sort of sell it to people, was taken from the original source paper. And in that instance, it was, I believe, so you have an initial omitted prefix column, which is on a column called departments. Then you have a range. Then you have an in. And then you have another in. So it's all kind of working together. You say it's like this sort of, and that's where I think it can make a huge difference when you combine all these techniques together, which you'll be able to do freely. So there, effectively, you have this query that would conventionally require huge and efficient index scan, which is just kind of a non-starter. What you would have to do is have a bunch of single column indexes and use some kind of bitmap or something like that. But then you give up the ability to do to have the sort order from the index. You can't do a limit 5 or something like that. You can't use a group aggregate directly, etc. Whereas this way, you can pretty well convert what you would think of as one big query into what you would think of as many thousands of tiny queries that each land on one if page again and again. And it's sort of a lot of small queries pretending to be one big one. It's not at all apparent to you looking at explain analyze that that's going on, but it is. So effectively, you're rewriting the query as if it was just a bunch of tiny queries in a way that is kind of fairly intuitively obvious. Like it wouldn't be very practical to do this, but you could sort of do it by procedurally generate a bunch of these small queries yourself, in principle at least. And that is the one sort of core clever idea here. It's surprising how far this one core idea will get you, because it is a fairly simple idea in the end. But, there's a bunch of things that I haven't even considered yet that the paper also contemplates. For example, it has a part about not in predicates. You would think it would be impossible to use a not in predicate for an index, right? But again, it's the same idea. It's like skip scan, except rather than enumerating every possible value in the index, it's enumerate every possible value in the index except these ones. So it's basically the same thing again and again and again. So it just buys you an awful lot. One core simple idea, which I find kind of cool. So that's the big picture. Yeah, it's something that I'm expecting to get into Postgres 18, and something that builds on work that started with Postgres 17.
So yeah, that's a great explanation. I think the multi-column thing is the complex example you mentioned is the part that blows my mind and starts to make me think, all this advice we've given that's, you generally advise people against huge multi-column indexes because they often only target then like a very, very niche set of queries. And you end up accepting that you're going to do a large index scan with a bunch of rows being filtered, which we know is inefficient, but it's currently the best solution.
You lose hot updates also. I'm going to continue advising against too many columns in index.
Well, okay, but I can see the flip side. This, like, once you only need fewer indexes, you don't have to support, like, let's say you've got 5 columns that are important here. Sometimes I've seen people index all 5 in 3 different orders to support different versions of, and I feel like that kind of thing will become less important if we even need it at all anymore. So that's mind blowing. But just to go back, your thought process is super interesting here as well. So did you come across this paper as like part of widening your horizons and then think of all these implementation ideas? Or was it you thought this is a blind spot for me, I should seek out papers in this area?
Well, there's surprisingly little written about the topic, actually, even though, as I say, it's implemented in a bunch of other systems like Postgres. I also think it's probably true that they don't exploit it to its full extent. The actual paper was written by people that were working on a system called Nonstop SQL in the 1990s, which it hasn't quite completely died yet, but it certainly has far fewer users. It was a very influential system, though. So I think that it's likely that the full generality of it hasn't been exploited for whatever reason in other systems. My hope is that my implementation will do just that. It's kind of weird. The example complicated query I gave, what I noticed about that is most of the time, if I change the order of the columns, not always, but most of the time, it made hardly any difference.
Wow.
Right, which is sort of like, that wouldn't always be true, but just given the particulars of the query that I'm talking about, like, it kind of didn't matter if I swapped, it made maybe a small difference in favor or but that is a bit mind-blowing, sure, that could ever be true. Again, it's going to be most compelling in cases where you don't really know what the requirements are ahead of time. It's very good for ad hoc indexing, and you can always beat it by having a dedicated index if you want to pay for that, but that's perhaps impractical for a lot of users. And again, I think on TP apps, it is still useful, but it's more for avoiding the worst case for something that you maybe should have anticipated but didn't for whatever reason. It's good for that more so than something that you would ideally plan on using. But it is relevant to both. As for why I don't know, I think it entered my awareness about probably 5 or 6 years ago, but I didn't fully understand it. And it took me a little while to figure out the right way of doing it. So having explained all that, it should also be pointed out that sometimes, whether or not you actually want to rewrite your query in this manner it all depends, doesn't it? It could be, for example, that the old way of doing it happens to be the most efficient one because, yes, you could in principle rewrite it into 100 different small queries, but those small queries would all be hitting the same few leaf pages anyway. So you actually would want to do maybe not 100, maybe 1 or 2 at most small queries there. How do you know ahead of time which it is? Well, you don't, right? But you don't have to. So I've had this intuition that if I solve that problem first, if I solved it for in lists, then after that, I would be able to move on to this. That would be a useful foundation. So Postgres 17, this has been implemented. It'll be available, I think, in 3 weeks when we release 17, if it all goes as planned. So that took the existing capability for indexing in lists and made it so that if you have 50 integers, say, and they're contiguous integers, it's like 1, 2, 3, 4, 5 through to 50, then suppose they're all co-located on the same leaf page, then you're going to do one index scan and read them all at once. If, on the other hand, it turns out that they're spread out all over the index because maybe it's low cardinality, or maybe it's low cardinality just in that part of the index There's no rule that says it has to be one or the other. It could be at different points in the key space. Low cardinality, others could be high. So making it a dynamic choice is very useful, I think, because you don't have to know. That's what makes it safe to aggressively apply these optimizations, because if it doesn't work out, well, in any case, the B-tree scan code is able to sort of combine the would-be accesses into one on the fly. So you'll get the same behavior as in previous versions, if and only if that makes sense. So that sort of flexibility, that dynamic behavior seemed like an essential kind of prerequisite. So it's not actually true. It's conceptually the case that you're rewriting the big query to lots of little ones that are, and then combining the result, allowing them to pretend that they are one big index scan, even though they're not. But the actual degree to which you do that, how much atomizing actually happens, is determined on the fly as the scan progresses. So it's kind of indeterminate if it's how many actual index scans you're doing, but that doesn't matter, if you get what I mean.
Yeah, it's so cool. It doesn't matter to the it's like one of those things that as a user, I don't have to worry about it, think about it at all. As somebody who's implementing it, though, it feels like it makes it much more complex for you to build. Is that fair?
Yes and no. I think there's two ways of looking at it. There's what you just said, which is in an immediate sense true. It is more complicated. But in another sense, it isn't, because complicated to who? I mean, the optimizer has to model all these costs, right? And it turns out that's hard. And it turns out that statistics are, well, they're statistics. And if you're talking about, like, you have all these secret hidden correlations with, these are multiple column indexes, of course. So we have statistics for each column, but at least unless you go out of your way to, there's no correlated statistics for columns. There's a generic assumption that these are independent, even though, well, very often they're not. So having it the access path be very forgiving. So the optimizer gets things quite wrong, but it actually doesn't matter, or doesn't matter very much at least, is way easier, at least from the point of view of the query optimizer. And on balance, that probably makes it much, much easier to actually, as a practical matter, make it work. I think that will probably turn out to be really important, although at this point, that's probably speculation.
I had this on my list of things that might come up, but the cost model's super interesting. It seems to me, and I haven't checked for sure, but from looking at some examples, like you might not have changed the cost estimations, at least in 17. You might consider that because you're making a bunch of things more efficient in a bunch of cases, you might try and reduce the costs for those to encourage those scans when they make sense. But I guess we're already doing, anyway, I guess my question is, have you changed the cost model? And if not, why not?
Yes, but I'm not surprised that you didn't notice it, because the main change that I made to the cost model was that now it'll saturate. Because, very simple observation, the most expensive possible index scan ought to be a full index scan. Very simple. If you scan every there's a maximum, pretty tangible maximum cost to index scan, at least in this world where this stuff is available, as it will be in 17, where it is physically impossible to scan the same leaf page a second time now, no matter how the constants have been specified in the query itself, because automatically that just cannot happen. It's a physical impossibility. So we know that we can take to the bank. And so the cost model saturates. There's an awful lot of uncertainty, except when it comes to the worst case. We know for absolute sure that in the very worst case, we'll scan every leaf page once. So that's where you notice it more. So you can have an absurdly long in list, and at a certain point, it'll just stop adding additional cost, since it is physically impossible for the cost to keep going up even as you continue to add these. So that sort of plays into what I was saying about having some general understanding of what the worst possible case can be when everything goes wrong, when the statistics are garbage. That assurance is, in the end, makes everything easier rather than making it harder, I feel. It's also just useful.
I like that. It seems pessimistic, but also safe.
That's it, exactly. It's sort of, I think of statistics as being kind of inherently just very, it's amazing that optimizers work as well as they do, I sometimes say. People don't realize, I feel often, when something goes wrong, well, it was next to a miracle that everything was working as well as it was for as long as it was. And probably things were not technically working optimally, but you didn't know that because you were happy with adequate performance. You didn't consider that that was technically 10 times slower than what could have, in principle, have been attained with the same index and such. So, like, I think that if we're honest, we have to admit that there's an awful lot of uncertainty about the cost models, and that doesn't necessarily matter. More and more, I'm encouraging the idea that it's amongst people that are on the hackers list that better to have a kind of, I wouldn't even call it insurance. That's too strong a word, but just have account for variation at runtime dynamically rather than doing so statically in the query plan. That just seems like, to me, something that has very little downside and potentially quite a lot of upside. It is a more general idea. It doesn't just apply here. It applies, for example, with, I don't know, you can do some similar things with hash joins. It does get more speculative if you keep going down the line of things that are like that. But why would you trust an uncertain selectivity estimate if you didn't have to? There's no reason why you can't have some kind of way of recovering from misestimation at runtime, at least in certain cases. I guess that it is related to that whole way of thinking about it. That is the projects I'm working on are sort of in that vein, I feel.
Do you mind if I break the structure a little bit as usual?
Go ahead.
I didn't read the whole discussion, so I'm going to ask some newbie questions. First of all, I see there is potential of, like, there is loose index scan as well, right? And this is a very different thing for distinct values. And we have wiki page, and we're constantly like using this technique. And we also mention, like you did, other database systems have it implemented. Postgres doesn't. But here we discuss skip scan, index skip scan, and this is very different, I see. But I just Googled a little bit and I found people use skip scan in that context as well, right? So if I'm right, some people reaching this point will still not fully understand what we discuss, right?
Oh, that's...
It's possible, right? So we discuss the problem. There is a problem. We have index on columns A, B, but filter is only on B, kind of first layer of like A is not relevant, and usually it means this index cannot be applied well.
Right. It's worth pointing out that with what I'm talking about, it only applies when you have at least two index columns, whereas I don't believe that's true with loose index scan.
Right.
You can still usefully skip if there's only one column.
Because there we need distinct values. It's different task. Here we need all values, but we have index, which usually we say you have wrong index, right? But your optimization will make it good, but only if a column has not many values, right? If it has a lot of values, maybe it won't be good, right?
It's certainly not going to be able to help because, of course, technically you could say, okay, there's a million logically distinct subindexes, but that is just degenerates to a full index scan, so it's the same. Yeah. By the way, that might still be the best plan, all things considered. We can't rule that out either. Sometimes that is actually the best available plan. But overall, you're probably not going to want to use it unless you have hundreds, perhaps low thousands, or occasionally maybe tens of thousands. But after that, it's unlikely.
Will the planner decide, will it have some threshold to decide when skip scan should be applied, when it already doesn't make sense?
Not as such, because as I sort of touched on already, there is no special skip scan index node. I think that's a bad idea because it's all dynamic, right? It's an additive thing.
Yeah, now I'm catching up.
Sometimes for all the usual reasons, you might want to have an index only scan that happens to use the skip scan, or you might want a bitmap index scan, or you might want a parallel index scan, et cetera, et cetera, et cetera. It isn't useful, I think, to have a distinct kind of index path. More choices means more wrong choices from the point of view of the optimizer. So I feel like that's a distinct advantage of the approach I've taken. Of course, I still have to figure out a way of making it not matter when that's not the right thing to do. And that's not very easy, but I'm almost, I think I've got that part figured out. We'll see.
Do you mean to minimize regressions at times where,
Because again, occasionally it's going to be intrinsically the best thing is to just scan the index without trying to skip at all. So you don't want to waste a lot of CPU cycles on a useless enterprise that is skipping when you shouldn't be skipping. You really do want to fall back on essentially the same behavior as previous releases there. Now, mind you, overall, it's hopefully the optimizer just wouldn't pick that way of doing it because it would be wrong. It wouldn't be the fastest available plan given the available indexes. So that only applies at all when you're already doing something that's basically pretty slow. But overall, yeah, I think I'm going to have to make sure that you don't notice it when it isn't able to do what you would hope it would. That is sort of complicated, for sure.
Just to make sure I've understood, if we could do a scan without skips, if we had the perfect index for a very efficient, let's say index-only scan, that would have been the index that would have been chosen in the first place because its cost estimate would have been lowest.
Right.
So already when we are skipping, you're doing a scan that involves some skips, we haven't had that available. And therefore, that's really cool.
Yeah. In general, I think it makes most sense to think about these sorts of queries as being on a continuum. One extreme is where there's, let's say, no more than 5 or 10 distinct. And then the fact that you're doing 5 different descents of the index is hardly noticeable. It's maybe less than a millisecond in the end anyway. So that would be a very favorable case for skipping. And then you have less favorable cases, I suppose, where the cardinality goes up. And eventually you get to the point where you can't do any skipping at all. And that's where you don't want to pay a penalty for being open to the possibility of skipping, if you like. Also, skipping, as I sort of touched on earlier, there could be, for example, that you have an index that has 90% of the pages in the index in respect of the leading column have 3 values total, but nevertheless, the remaining 10% are all perfectly unique. So now you don't have, you can't really average the two. It's just 2 different things. You can't think of it as the average of the 2, really. So the fact that it's kind of continuous just sort of kind of makes sense. You wouldn't want to have it be, if the planner were to make a static choice, then how would you account for that variation where you legitimately need to change your strategy for the same index scan in real time? That's totally possible that would be the best thing to do. So by not having an opinion until you really have to have an opinion at the last minute, you ideally get the best of both worlds. That's the thinking anyway.
I think it's super smart. And those distributions are quite common. We see them all the time. And it's the time where statistics most obviously falls flat on its face because of averages. And anyway, I know it does some things to most common values and things to. But anyway, completely agree. That makes loads of sense. Sorry, you were going to say.
I was going to give another example of what you're saying with statistics. I mentioned briefly earlier, there's this, I think it's called the attribute entity independence assumption. It's this generic sort of assumption made by all cost-based optimizers that there's no correlation between different columns, which is demonstrably false all the time, but somehow mostly doesn't break that badly. But for something like this, you got to think there could be a very strong correlation between columns, or there could be a totally different, completely independent relationship between the two. And it's really hard to model that. So if you can just not do that to much of an extent at all and still get useful query plans, that seems ideal. There's just different types of indexes. So you have, for example, in the paper that I talk about, it's data warehousing. So you explicitly have different dimensions of a business that are obviously quite independent. But then you could also have something like, I don't know, supplier ID, first column, second column, discount code. So it might be that different suppliers use the same discount code coincidentally, but even then, those 2 discount codes are completely distinct entities. So it just doesn't make sense to think of them as being the same at all. You wouldn't expect a query to just supply a predicate that doesn't have a supplier ID. You would expect the supplier either to have a supplier ID or have both. You wouldn't expect it to be omitted because it just kind of wouldn't make sense. So it's impossible or very difficult in any case for the optimizer to understand those kinds of distinctions, even though they're obviously very, very common. So again, ideally, it wouldn't have to. Ideally, it would just be able to fall back on this sort of idea of, hey, we'll try to work it out at runtime to the best of our ability. As long as we have get the fastest query plan, everyone's happy. It doesn't necessarily have to be that exact a cost model. In fact, it usually isn't. So that's kind of the overarching philosophy of the thing. And
yeah, as usual with your work, it's so simple once you understand it. But I'm super impressed with the thought process to have got there. It feels like yet another feature where, as users, we don't have to think about how it's working, why it's working that much. Maybe with strategies later in terms of indexing, we can take advantage of that. But we could carry on indexing exactly the way we are, and we'll only benefit as a result still.
Unless I mess up, of course, but hopefully
Yeah.
I do that.
Yeah.
I'm not exactly playing to my strengths when I'm talking about the optimizer, you understand, but nevertheless, that is kind of part of the philosophy. I'm not really an optimizer person because I like being successful. That's probably why. But here, I think that, undeniably there is some thought given to those aspects because it kind of has to be.
What do you mean successful?
Well, it's just really hard to do anything in the optimizer. That's why some people do. And thank goodness someone is willing to do it. But it's a very difficult area to work in, I feel, which does seem to put people off more than perhaps it should. Perhaps that will change at some point in the future, but you have to ask somebody else about that.
Yes, that somebody else, I believe, is going on another podcast soon, which I'm excited to listen to.
Oh, great. Oh, I think I know what you're talking about.
Yes. For everybody else, this is Tom Lane going on the Talking Postgres podcast, which is scheduled to be live, I think, next month. So I'll share a link to that. Exciting times. So you've talked about it briefly already, but another cool thing you've done here is split this work into some useful stuff on its own for version 17 coming out soon. I'd be interested to hear, how and when did you realize you could split it up into the in-list optimizations that I think are going to be very useful for a bunch of often generated queries that people don't have that much control over, relatively in lists seem to pop up, at least from what I've seen from ORMs normally. How did you work that out?
I'm not sure exactly when. I think it probably wasn't any one moment where I realized that those were. I remember talking about another patch, actually one for Lucid NextScan, and just being very confused about that whole area myself, being very confused about what the difference is, where to draw the boundaries architecturally. And I recall asking to nobody in particular at the time, how does this relate to in lists, or what we would call internally scalar array up expressions equals any array expressions? There must be some relationship here. At that time, I was aware of the paper, the source material, and that strongly suggested as much. But I kind of thought, you can't really have an opinion about one without having an opinion about the other. You want to be able to combine these things arbitrarily. So that was when the initial awareness sort of sunk in. Then I did some work on Vacuum over a couple of releases, and I came back to B-trees again. And I think at that point I realized, okay, this is probably the most useful thing I could do. And then I think I kind of got a little bit lucky as well with the project for 17. I worked out a couple of things on the optimizer side that I wasn't necessarily counting on. That's more subtle. It's stuff that's related to whether or not we know that the scan will return ordered results. So I realized the relationship between that question. So in previous versions, you would do a query like select from table where A equals 5 and B in a long list, order by A, B, limit something. And it would be able to terminate the scan early because for reasons that are complicated and not that interesting, the implementation could trust the B-tree code to correctly return things to the ordered results. So I had this idea that was important, but I didn't know how important it was to everything else. So I kind of got a bit lucky in figuring that out in about 2023. Before I even realized that I was pretty sure that I would do the skip scan thing, but there was some amount of serendipity with, there was actually a user complaint. I think it was on Slack.
Oh yeah, Benoit.
That's right.
I'll link that up as well. Yes.
Yeah. Benoit had a complaint. Basically, because of the limitation I just mentioned, the query plan, which was for such a query with a limit, it couldn't do it without creating a way of filtering the out non-matching rows that required heap access. So for reasons that are not really fundamental and worth explaining. It did way more heap accesses just to exclude non-matching rows, when in principle it could have done that at the index level before accessing the heap at all. So for very roundabout, hard to explain, and actually not that relevant reasons, that made a huge difference for his use case. And I wasn't even thinking about, because I'm a B-tree, I wasn't really thinking about avoiding heap accesses. But then I found, actually, that's by far the main reason to do that. I was thinking initially about just the simple fact that, hey, do you want to do the index descent, 1 time or 100 times? Obviously, you want to do it 1 time if that's feasible. That's where I started. But then I realized, not much later, but somewhat later, with some help from Benoit, actually, yeah, you can, in some cases at least, completely, owing to all this roundabout nonsense with restrictions in the planner, you can completely, for some cases like the one he showed, you can completely eliminate a huge number. And that was by far the best, but the most sort of flattering case for the 17 work, where I think it was like 20 times faster, something like that. It doesn't really matter what the number is, just way faster, because you're fundamentally doing way less I/O. So I didn't necessarily count on that happening at all, and then it kind of did without my initially realizing it, which was nice. Serendipity did play a role, as it often does.
Very cool. Nikolai, do you have any questions?
Of course, I have comments and questions. All of them are silly, maybe. Once again, we should avoid this confusion. Loose index scan is not skip scan, because I saw posts about mixing these names, but I double checked Oracle and SQLite, and they have both skip scan, the same meaning, so we should stick to this.
I guess so, yeah. I mean, I wouldn't mind calling it something else entirely, but right. I certainly do think the distinction between loose index scan and skip scan, I mean, I was confused on that point myself. I mentioned this already. The important idea to me, the important distinction between the two is, so loose index scan involves an index scan that knows specifically that it's feeding into a group aggregate. So it's only correct because you don't actually logically need to return all of the rows from the index, or indeed from the heap at all. It's only correct because of that high-level context that you're applying in this low-level code. Whereas, in contrast, skip scan isn't like that. Skip scan is just exploiting information that's readily available to the scan. Right. It's doing index scan things in a more clever way without really understanding how that information is being consumed 1 level up or 2 levels up. So that's how I think of it.
Yeah. You mentioned work on loose index scan also happening. What do you think about future of that work?
I think it's a perfectly fine idea. There's nothing wrong with it. I did briefly look at that some years back. My recollection of exactly how it was at the time is a little bit vague. I remember noticing that it had lots of planner stuff, which, that was probably a little bit of something that discouraged my involvement, because, again, I like being successful.
Right. Yeah.
But I mean, fundamentally, it's a perfectly sound idea. It's obviously a good idea that could be implemented with enough effort, and I think that the patch didn't have any major problems, or at least didn't have any major problems that could not be addressed in the fullness of time. I recall Tom at the time, who was sort of asked to take a look at it by me, saying it was maybe doing things the wrong way in the planner, but that's kind of above my pay grades. But, from an indexing point of view, like, it's obviously it makes sense. It's like, just thinking about it very, very sensibly, it's doing potentially an enormous amount of I/O. You're potentially doing an enormous amount of extra I/O that you don't need to do logically. It's not. Yeah, I mean, it's inarguable that that's a perfectly good idea. If I haven't started there, or I haven't paid too much attention to it, it's only because of competing priorities. It's not. I think it's totally reasonable.
Yeah, we write with Recursive all the time to implement this, basically at application level, right? I'm curious if there are any specific benchmarks which could be helpful for these both patches to check, like, kind of workloads.
Well, not really, because as often is the case with things that have some planner component to them, it's sort of like, it's perfectly obvious that it's not a quantitative improvement, it's a qualitative improvement. So you name a number and I'll give you a test case that is faster by that amount. It doesn't make up a number. It's no problem. I'll get you a test case that'll do that. I just have to come up with something that has, sufficiently large amounts of things that you will be skipping now versus just does it. So
Right.
coming up with a number, it's not really very meaningful. It's just you're doing it in the efficient way, the obvious, sensible way, having not done that. So there's really no practical limit on how much faster it could be. And it's hard to make generalizations in the real world that
Right.
apply in the real world. So that's kind of the annoying answer to your question.
By the way, I wanted to ask you about propagation of this idea from B-tree to other types of indexes, GIN first of all. Is it like valid idea at all? Maybe with combination with B-tree GIN, right? Because
it definitely could be, but then the way that GIN in particular does multi-column indexes is kind of weird. The way that actually works is it essentially, rather than having a B tree that has A and B stored together, let's say it has a B tree, if and only if you have a multi-column index, it has a B tree where attribute 1 is stored with 1, whatever the value for A is, and then attribute 2 is stored with 2, whatever the value for A is. So the column number is in the B tree itself, where the entries live, is the most significant key, which is very different. Now, if you said to me, what about GIST? Then that's very different, because GIST is much more like B tree, particularly here. I think with GIST, it's totally possible. The way that GIST works, so the source paper I mentioned, efficient search of multidimensional indexes, you might be confused. You might think, well, multidimensional like GIST? And the answer is yes, sort of. I'm doing work that's purely enhancing B trees, but some of the ideas with dimensionality are, at least at a high level, related to things like multidimensional indexing using GIST. So I think it's entirely possible to do that. GIST is loosely ordered, so it's kind of inherently doing something a bit like that anyway, right? Where it's not so much finding the exact match in the exact place where it must be, but rather looking in all the places it could be exhaustively, which is usually only a fairly small number of pages. It doesn't have the same propensity of B-tree to go to exactly the only right place for that value that you're looking for directly. It's more because of the loose ordering of the index. It's not quite doing it that way. There's a bounding box in the internal pages which describes what the leaf pages contain. So you might have to do 2 or 3, even for a point lookup, you might have to do 2 or 3 leaf page accesses, as opposed to just 1, which would be very often the case with the B-tree. So it's almost kind of doing that anyway. So it seems entirely plausible that with GIST you could do something similar. I don't think that's probably possible in the case of GIN, though, because what does that even mean in light of the scheme with GIN storing 2 different attributes in completely different places, and the tray doesn't really seem compatible with that. I don't know, though. I mean, anything's possible.
What if it's B-tree GIN when first column is scalar column, like organization ID or category or something, and second column is like JSON-B or something?
Maybe. I mean, I think it's probably more fruitful to talk about it in the context of a use case. So there, I guess, intrinsically you have a kind of nested structure to JSON. And so having that capability could be useful if you had some kind of partitioning scheme or something like that, I suppose.
Oh, I mean, JSON nested structure doesn't matter. It's second column.
I know.
Right? We put scalar like value, like some number or timestamp on the first place.
Yeah, I mean, I think that could be possible. I haven't thought about it too much, though. You have to talk about it at 2 levels as well, though. It's like, what would be like sort of practically achievable within a year?
Let me tell you.
What could be.
Yeah.
Okay.
Why I care so much about this?
All right. Yeah.
Because I started to reflect one problem recently related to full text search in Postgres and why people move to Elastic. And why I did? Because I saw a similar situation happening with pgvector. Because, the most popular issue in pgvector repository right now on GitHub is additional filtering. Mm-hmm. So people need the global index with vectors, but they also need to be able to sometimes search locally for particular project, organization, I don't know, anything. And this usually is done what Elastic and others, they call it metadata search. Basically, it's additional filters, usually scalars, like numbers or timestamps, something. And B3 for vector search is not solved yet. That's why people still consider, like they say Postgres vector search with pgvector is not well for us. Because usual solution is let's just create partial indexes. But if you have hundreds or thousands of categories, it doesn't work well. And then I realized that for full text search, we had similar problem for years. And usually it's solved by extension B3Gene. And then you are able to create multi-column index. But this is a barrier for many people. Although this is a contrib module, it's present everywhere. It's some kind of a barrier. And I saw cases when people even created this extension, but somehow still not using it well. Like they still have this problem, B3 versus Gene dilemma for Planner, right? So I'm thinking, yeah. And I'm thinking if we, for example, if we use B3Gene more often, we usually will put scalar value on first position because it's more selective by default, maybe. We don't know, right? And if it has a low number of distinct values, this skip scan approach would make total sense there as well, right?
Maybe. I don't have a lot of domain expertise here, so forgive me. I need to ask questions to clarify what you meant. Yeah. Are you talking about like pushing down a limit for each grouping or something like that?
Limit is like I'm not sure about limit and ordering. I'm just thinking,
but not a limit for the entire query, but rather for each individual grouping or whatever, where you want to. Is that related to the question?
Imagine we have full text search, TS vector, gene index, and then we have additional thing like, for example, creation time, and when we want to search within some window only, right?
Mm-hmm.
By default, full text search in Postgres doesn't support it itself.
Okay.
It will be different B3 index on timestamp, like created at timestamp, and we have global whole table gene, right? And then Planner decides what is cheaper, B3 and then filter on the fly, or use full text search and then filter or order by on timestamp. And B3 gene extension gives you opportunity to combine, have 2-column index, and then the goal is to find everything and no limits, right? But if we put scalar value on first position, queries which don't have this filter will be like not good with this index, right?
Mm-hmm.
So we put timestamp as our column A and the TS vector as our column B. Use B3Gene for that to have 2-column index, right? And then I would like to have skip scan for this because if my query doesn't have additional filtering and we have low number of distinct values for column A, right? Maybe timestamp was not good example because it will be a lot of distinct values, right? Let's say it's some category ID or I don't know, like group ID or something. In this case, probably skip scan will help there as well for such queries. Or I'm forced to put this column to second position and keep full TS vector on first position. Okay, this is something to think about it. Additionally, I'm just very curious.
Yeah, I don't know is the simple answer. In principle, you could, after all, what I've described is in the end, there's a bunch of details, but it is basically quite simple. You have to be willing to do, at least in the simple case where you've fully omitted a prefix column, you have to be willing to look at every single individual partition, every distinct value, which adds up quite quickly if it's something like a timestamp. Whereas I think if you had some kind of bucket by day or something like that, then it would be more feasible, because then you would have relatively few buckets, and it would, especially if you had not completely omitted the date column, if you had a range of between, say, then it would be, I think, feasible from a data structure point of view, not necessarily in Gin, but in something to do something like that. I don't know what the basis of comparison here. What is Elastic doing? I just don't know. I can't speak to that.
Know as well, internals. They just claim if you have additional filtering, it's not slower at all, and usually it's faster. This is what their documentation say. I'm very curious about internals as well, because I just feel this, even from user perspective, even the need to create B3 Gene extension it's already a barrier. Some people don't do it, and they think, okay, full text search is weak, and they are going to have the same impression about vector search. And this whole topic about combination of these powerful indexes with B-tree indexes, it's interesting direction, and I think can be improved as well. And with SkipScan, maybe it can be improved further. This is my basic idea. It's quite maybe not well thought. I promised to have silly questions, so
it's okay. There are no silly questions. Well, I've got an even sillier idea because I have I think a very, very Fisher-Price level understanding of how PG vector works, which is not going to do much good here. So, I'm not going to say something about I think I know so little about. It's something that maybe I'll talk to Jonathan Katz about it next time I see him. He's my go-to expert on these things. He's very happy to talk to me about.
I'm sure he knows already this problem very well because, as I said, this is the most active discussion among issues on the repository, and basically all people need this. They need the combination of B-tree and vector search somehow. Maybe not only just one B-tree column, not only Scholar, but a bunch of them, because they need to filter additionally. And this is a challenge. I also know one project which they built some kind of quite universal solution for the others. And when they first came to us, they said, we are forced to index every column because for flexibility. We know this is anti-pattern, but we are forced. And I'm sure they will be happy when Postgres 18, if it's out with this optimization. This is super relief for them because they are struggling with this problem. It's good to index to have only, as Michael said, only one index on multiple columns and don't think too much about order.
Yeah. Especially if, as I say, the important distinction is between getting very, very slow, totally unacceptable performance, typically sequential scan of a very large table, versus adequate sub-second, but not sub-millisecond. A lot of people are in that zone, and if they have a lot of ad hoc queries, they can't really predict the needs of indexing needs ahead of time. I think it makes the biggest difference there. Much less so in OLTP apps, but still to some degree, it's going to get you acceptable performance where you didn't know that you really ought to have had a certain kind of index. And then you get adequate-ish performance there too, which could make all the difference in a pinch.
Yeah, well, actually, interesting additional question I have. Maybe with loose index scan, we have this wiki page describing this technique. We apply this technique using recursive CTE, right? Mm-hmm. And there is a expectation in the future we'll stop doing this. It will be fully automated. Does it make any sense to think about implementing while we are still not there and not on Postgres 18 and it's not even committed, right? It doesn't make sense to try to implement similar approach at higher level ourselves somehow, splitting query to pieces like different index scans?
It might. I would just say, in the case of if you're able to upgrade to Postgres 17, and having done that, you're able to also, suppose you have 10 distinct values in your leading column, if you can write an in list that has those 10 distinct columns and are satisfied that will work for you, that'll give you the correct answer, not only when you write the query, but going forward, if it's sort of static, then you could totally do that. And in fact, I would expect the actual access patterns to be identical to what you would have gotten had you had the skip scan feature or anything. It is basically doing the same thing. It's just rather than having an array with these constants that come from the query, you would instead have a magical sort of an array that the B-tree scan code uses almost the same way. It's just that it generates its array elements procedurally and on demand, but it is essentially the same thing at a quite low level. So it would be not just similar, but identical if you could, make it work within those constraints. And in particular, there'd be no possible downside in terms of whether or not it made sense to do a full index scan. Depending on the distribution of values, it's going to be adaptive in that same way I described. With the big caveat, of course, you kind of need to know that the at least for those leading values, that it's static and predictable. They won't change and break your query. Yeah.
So I guess our approaches will change with this. Usually we analyze workload and decide on indexes. We decide what to put on the first position, second position. Here it seems like sometimes we will decide to put columns with lower cardinality of distinct values or something, right?
Yeah. That'll start to make way more sense than it did. I don't want to overstate it. I don't want to say it's not like a revolution by any means, but there are specific rules of thumb that will be weakened by it for sure. One that you already said yourself, Nikolai, was put the highest cardinality column first. Well, that's already kind of suspect actually, but it especially is in this world with this capability.
Interesting.
I think it's mostly confined. That'll be most true, but by far with more your data warehousing use cases where there's a built-in requirement for a lot of ad hoc querying that you can't really exactly predict ahead of time. Looking at the detail of something rather than just a summary really matters. Then yes, absolutely, that will be true. Well, with OLTP apps, less so.
Cool. Yeah, this is interesting direction to explore, even if patch is not yet committed. Thank you. Go and
thank you for having
me. Have something in to-do list, right?
Yep.
Is there anything else you wanted to make sure you mentioned, Peter, or anything anyone can help you with?
Well, I always welcome input into the work I'm doing. It would be kind of nice if I could get some feedback on the stuff we were just discussing about, hey, how as a practical matter does this alter the general advice that we give to you about how to index things? I'm not entirely sure how in practice that'll tend to work out anyway. It is nice that this is a very general thing. I think that'll tend to make it possible to use it more often because in a certain sense, the optimizer only has to have the right rough idea, because if it has that, then it will pick an index scan and then the index scan itself will figure out what to do. So I think that's probably going to make it more compelling than it appears to be in other systems where, as far as I can tell, I might be mistaken, they require the optimizer to generate a distinct index node type. So it's kind of either or, which seems to be anyway could be something that limited the applicability of the optimizations. So I feel like it would be nice if I had a better idea of how, practically speaking, this will change things and where. I don't think I've got a complete understanding of that myself. Like what kind of applications, what kind of usage patterns. That would be nice to have more detail on. So if anyone wants to help me, that would be an obvious place to start, I would say.
Nice. Thanks so much, Peter. It's been an honor having you on. Great chat.
Thank you both. Thanks, Michael. Thanks, Nikolai. I really enjoyed it.
Thank you. Have a good week.